A very warm welcome from our side here from Schlotau and Bauer to a new webcast. We are really happy that you joined us today.
Let's have a start. Of course, you know our company, which is Schlotau and Bauer. It's a company which exists since 30 years. It was founded in 1991 in Berlin with more than 100 employees at 6 different locations. Of course, we are famous in traffic design, traffic engineering, and consulting. And of course, and this is really famous for Schlotau and Bauer, the software developers, which made the tools for traffic engineering and so on, are directly beside our traffic engineers. So we are really close to tackle the problems we have with the software we developed. So traffic lights and traffic lights state of the art. From a LISA perspective, it is so we have a fundament first when we implement an intersection, we have some kind of a fundament which is most of the time a fixed time signal control. This is just a fallback which can be more dynamic with a traffic actuated influences in it, and also you have a fixed time control maybe to optimize the coordinated networks. Means that the time gaps between all the intersections are handled as a kind of a fallback, which can be more dynamic if you bring it together and just do interaction between that intersections. Then to be traffic actuated, you need detectors, of course, and most of the time those detectors are at fixed locations like induction loops, like cameras, CCTV, radar, and so on. You measure the traffic at a specific point in your network, and this is all you have. Next to that, you have traffic actuated signal controls, means that you interact with some kind of a plan where you do some green term distribution, phase changes, and so on. But you can also recompute the whole signal programs just to adapt fully to the current traffic scenario. This is state of the art right now. In LISA itself, we are most of the time using phases, and for phases, we're using different kinds of interactions. This is the phase request, maybe for a pedestrian. This is the green time distribution, of course, to have the green time at that saturation, which is currently at the intersection, with phase changes, and of course there are some special phases, especially for the public transport. At controller level, the control algorithm, the traffic light algorithm, is processed in Germany every second. Foreign countries, these frequency is a little bit higher or can be a little bit higher, but every second in Germany there's a recomputation of the signal logic. There's a check if a detector is occupied and so on, and then you have an effect in the traffic control, get more green time or whatever. Coming to the point that we are having a new kind of information source, and this kind of information source are connected vehicles. Here we have two sides to keep in mind. The first side is that there's a connection between vehicles. This is the car-to-car connection or vehicle-vehicle connection, which was developed to ensure the quality of the traffic flow and of course the safety of automated cars or connected cars. This is done with a cooperative awareness message, a CAM message, which have a radio or range a couple of 100 meters around that car. And the content of that message is you have got a position of the car, the current position, the speed, the priority, the vehicle type, if there is a siren on it or not. When an automated car tries to handle the traffic in an urban area where there's some intersections, you have to make sure that the automated car can determine the current signal state at the intersection, which is really hard to handle with current kind of sensors you have in the car. This is the reason why there are some more messages coming directly from the infrastructure. The first one, the most important one, is the map message. In the map message, there is the topology of the intersection included, which means the ingress and the egress approaches, the connections, the relevant signals, the restrictions, max allowed speeds, and so on. Next to that, or related to that, there's the spot message, the signal phase and timing message. So you get the current signal phase, so you can make sure that the automated car can stop at the stop line because it can fully understand the current signal, And next to that, you can have a look in the future just to see what's the effect of the intersection in the upcoming minutes, seconds. And because of the actuateness level of that intersections, there's the prediction needed. Because the timings of the signal phases are directly related to the traffic scenario and the traffic flow at the intersection. Means that you get 3 or 4 different values. One is the min value, so the min time when the current signal light can be aborted, signal phase can be aborted, max is the maximum, and the likely, and this is directly the prediction. And of course, a confidence value just to make sure that you know how good your likely time will be. Next to that, there are some new messages here. One of them is that signal request message. This was made for the public transport and also for emergency vehicles. This was made to have a prioritization at the intersection, mean that the car can bring up some message to the intersection itself, says that it will cross the intersection from that direction to maybe that or that direction, and wanted a prioritization at that intersection. So the intersection control will get that message and give an answer, and this answer is included here. It's the signal status message where the intersection can answer to that request directly to the car. So the car knows exactly, oh, I will be prioritized at that intersection in the next second. So this is the most important messages in that field. For the map message in Lisa, there's also export functions. You can model your intersection in Lisa. This is part of the fundamental data, the base data, where you model your intersection just to construct your signal-light logic, and this is exactly the input to build the map message itself. This is some kind of an XML structure. This is not not the message which will be transmitted directly to the car. The reason for that XML output is the reason that all the values you see here, the lane set, the lane width, reference points, connections, and so on, are part of the real message, the binary message, which is broadcasted to the car. That means the export of Lisa goes directly to the RSU. At that place, the roadside unit, it will be parsed, it will be interpreted, and then the real message, I would call it a real message, so kind of a byte stream, is constructed and pushed directly to the car. So state of the art. Next, the signal phase and timing. So the current signal light and of course the prediction of the next signal switches is done in this bed. And for that we have a process in Lisa where we can have local predictions. Means that you don't need an external provider to get your SPED prediction. You can also do it in Lisa itself. So I think this is a really good place to put in the prediction, because here you don't have any loss of latency, because you have no transmission of any data to any cloud provider or whatever. And next to that is that with a prediction with Lisa itself, we know all the variables, all the decision points, all the steps you did in your unique logic. We see that, and we can handle that in the prediction itself. And then you can have services like a Glosa, a green light, optimal speed advisory, and you have a nice intersection assistance here. So what are the potentials, or why should we as a traffic engineers think about the CITS components and how we can use it in a infrastructure for the infrastructure? The first thing is we can have really early stage requests. If we can use more than the locations of the detectors we have to detect that there's a request, we can use it and we can handle it directly. Next, we can have optimized green time computation and efficient green time redistribution. The reason for that is if you can determine the current traffic scenario better and better, you can react more actuated to that than the situation we have right now. Right now, we do a lot of assumptions just to make sure that we understand the traffic scenario, the current traffic scenario well enough by the detectors we have. Next is we have optimized stage sequences. If you have a look on a brighter scope, you can also have a network's dynamic green waves and the prioritization of public transport and emergency vehicles. Also in a bigger scope here. The usage of CITS information in LISA is or maybe was then with some kind of a model. It's called a vehicle buffer. It's just a name. Um, and in the vehicle buffer, we see the point that we don't want the current messages of the car, the binary blob messages which comes up here. What we want to have is we want to have the information we need to write signal logics in a way we do since in several years. We use information, we do a decision, and then we bring it to the intersection to the light. So what we want to know is for each equipped vehicle, we want to see on which lane is it, which approach. Maybe it's a bit rougher thing here. We want to see the distance to the stop line or the estimated time of arrival. We know that they car in 10 seconds. We can do everything just to ensure that they can cross at that time. We need to see the current speed so we can compute the level of service, for example, the vehicle type, the length, routing decisions if it's available. If there is an active siren, so we can do emergency prioritization, and of course if there is a public transport here or not. And just to get to have a really simple view on how we model that data, you see here it's a table. In the real world, it's much more complex, but with a table view, it's really nice to explain. So each vehicle we can detect here, it gets a unique number. So you are able to track that vehicle over time. Then in a map matching process, you get the ID of the lane. And with the map message, you know where it is, where the lane is, and which signal group is responsible to that. You see the distance to the stop line, you see the current velocity, and you see the priority of the car. All that information you can directly use in the signal control right now. How can we get CITS information? And in Germany and the rest of the world also, there are two main approaches here. The first one is on the right side here, the decentral approach. Means that you have a dedicated short range communication, means in the directly surrounding of the intersection, you have message exchange here with the between the vehicle and the traffic light, the roadside unit, sorry. Means you get the information directly here and you can interpret it here. This is the roadside approach, and the central side approach on the cloud base means that you use cellular networks to exchange information, mean that you need a base station where all the information are collected. You need some servers, maybe it's an edge solution or a cloud solution, and then you need some wire back to the controller just to make sure that the information are available for the signal control. And currently we have the state here that if you're using cellular networks, the content of the messages here are really specific because there are less standards in that area. The communication is standardized. Communication means the wire back to the controller. In Germany, it's called Anwenderparameter. So it's parameters you can pass directly to the control. There's a standardized way to that. Or maybe you can modulate that information and use it as an input detector or whatever to the controller, just to make sure you can pass the information directly to your signal controller. And on the other side, on the RSU side, the content is standardized. There's the CAM message, the SPAT, the denim, and so on. But the communication is really specific. Means the way from the RSU to the traffic light controller are really dependent to the vendor of the controller or the RSU. So just bring both worlds together, the central approach and the decentral approach. Here we have the TLS controller here, the OMTC, which is a library of Lisa. It's a standardized library. And then you get the user methods, and the standardized OML library. With that image, you have the opportunity as a user. Oh, I'm sorry for that. It's German. It's the control, the signalized control here. You don't have to take care about the communication way and how you get that information. If it's a cloud solution or a decentralized solution or whatever, the methods you will using in your code will always be the same. There's no difference to that. So in the past, we extend Lisa, and with the upcoming new release, Lisa 8, you will see it also. Now we have a virtual traffic light controller. We have virtual RSUs in the uh, in the network there. We have OML methods, so they're the user methods you can use in the code in the traffic light logic, where you can use directly information of cars and public transport and so on. We have test and debug functions. Also a mistake here, sorry for that. Debug functions where you can write your code and just check it directly in the simulation with a penetration rate like 1%, 10%, 50% or whatever, and see the effect of your control. And for the level of service you will reach with the extension, with the extraction of CITS data, and of course there's the simulation. Just to have another point or another view how it looked like in Lisa 8. You have your it's called Lisa Testplatz, the test suite, the test environment we have here, and you get all the information of each equipped car. You can track, you can observe what's going on here. You can point directly back to the code, see how the effects will take in place, what you can change with that information about connected cars and so on. So it's a really cool tool. It's, for me, it's more like an IDE. It's some kind of a programming interface. You can do changes, simulate, go back, verify your code, just check it again. And in the end, you transmit that data or the signal program directly to the controller and make sure that the RSU or central is connected, and then you will have the effect on the streets. Just to give a small example how you can use CITS information and signal control. Three approaches: two conventional and the new one. The first one is you can use the detector which is directly in front of the stop line. It's the detector for the occupancy of cars. So if the car reaches that detectors and we have an occupancy here measured, we are at signal K1L, means we have a request here, then we have some minimum time, some intergreens, and then we can switch. Means that the car which is occupied here have to wait 10 seconds. The first approach. The second approach is if we are using the detector which is responsible for the time gaps, for the time gap control, or from a camera or whatever, you can have the request really early, just a few seconds before the car is reaching the stop lines, and you can just avoid some seconds of waiting time for the car, but not all. So the car has to stop directly here. And now there is some new technology. The CITS information means that you can track the car, and if the car is as close at the intersection that you decided to use that information, you can bring it in the control. So we have the request here because we are 12 seconds before the stop line. And then we have our intergreen, and then we will have directly the green when the car reaches the stop line. But just to make that clear, in that case, we have a car which goes directly to a red to a red signal, and so the car will will decrease the velocity. But if you combine the control of the intersection with a correct SPAT information, with a correct prediction, and it will be correct because you made that decision already in the control, you can have a really great traffic flow here. But this is only possible if you have connected devices here. So we can reduce stops, avoid waiting times. It's also relevant for vehicle and vulnerable road users. And the effect you will have with the first vehicle, it's not part of a 1% a penetration rate also on. With the first vehicle, you will have exactly this effect here. Just to give another use case here, it's the dimensioning of green times. Mayuki, you have a question?
Just for the last slide, from the last slide.
One goes back here.
Yeah, here in this case of CITS with 12 seconds, we are talking about green time extension, right?
No, this is the estimated time of arrival. 12 seconds before the car is will hit the stop line. So you can use it, and then you have to make sure that you can use 12 seconds in your signal program.
Okay. Okay.
You have to handle all the traffic streams, of course. The next one is a typical time gap control at intersection. Means that you have detector here. It's right 3 seconds before the stop line. And if you measure that the time gap increases, it means that the platoon before the on the road will be over, so you can stop your green and just use it for a secondary road or whatever. So this is typically the conventional time gap criteria. But the problem here is if you measure the traffic exactly at that position, you cannot see what's coming next. This is really a problem. If you have a lot of traffic on the road, you will decide here just to stop the green, and all that vehicles which comes up here will stop here and have some waiting times, wasting some waiting times. Then you can have CCAM. CCAM is just another abbreviation for CITS. CITS means Cooperative Intelligent Transportation Systems. CCAM means Cooperative Connected Automated Mobility. It's just maybe it's a bit more than CITS. So, and if you have a high equipment rate and you can measure all that vehicles which is on that road here, you can do just a really easy computation here. So what you do here is you do the division of the number of cars here with a specific time slot you have, and if the amount of time for one car is below one given number, like 2 or 3 seconds, you can decide just to increase your green or decrease your green. So stop it here. So in that case, you see we have enough vehicles that the amount of time for each vehicle is low enough. So you decide just to extend your green with 100% penetration rate, of course. And for the last approach here is we have CCAM, but we cannot measure all the vehicles because they're not equipped. So old cars here, one here. So we do the same equation, just check how many green we need per car, and we see, oh, it's too much time for each car. So we will also decide it just to stop the green here. So means compared to the conventional time gap criteria, there's no change here. Change we have here. But to make sure that you don't need that high equipment rate, because they are really, really future, that's really part of the future, there are more messages. I didn't talk about that. This is some CPM, where other cars can see also the surrounding of the cars and just measure that there are more cars. And you can use that information also from the intersection side. So there's no negative impact. You can decrease the waiting times and of course reducing the stops. How you can use it in our diagrams or our logic editor in Lisa. You can have a simple logic. That ZL means time gap of a detector. So if this is just a really easy thing for a time gap control. So we check one detector. The detector name is D2_1. Means if the time gap of that detector currently is greater or equal like a constant of a constant, which is maybe 3 seconds, we decided, okay, the variable time gap ZL for K4 is true. Means that we will stop the green in the next couple of seconds. But now we extend that time gap control here with a loop over the equipped cars which are on the road. Means we have a loop here where we check if there is a car on a specific line, that's line 4 here, and we see, okay, if there is a car on line 4 with an estimated time of arrival below 5 seconds, we will deny that criteria here. So we set that value to false, And then we will make sure that that car which is detected here will also join the intersection at green. So this is just an extension of a given control by CITS, new CITS functions. Of course, in Lisa you will simulate that new stuff. Means that you get that CCAM information, you can observe it, see it in the control, you can bring it to text files or whatever you want to have, Excel or whatever. And if you want to go further, just to simulate maybe bigger networks where we have a couple of Lisa controls with that V2X extension or the CITS controls, you can also use PTV Visum. And the last year there was an extension made by PTV Visum where we can exchange the data, the necessary data we need from the simulation directly. So you can use also the CITS methods in Visum. Next, of course, was a good year last year. We had the first real-world implementation done in Düsseldorf, Germany, where we put the concept of the vehicle buffer directly in the Lisa signal control, connected it. It was an Actros controller from Swarco, and connected that to a roadside unit also from Swarco, and of course there was a connection to a traffic management central. So what we've shown there is that we can run two approaches at the same time, the central and the decentral approach. And the great thing here is that it's fully transparent to the user. Means you can use exactly the same method, and the only thing here is that the communication, the way you use the communication is changes. But this is not important for the user. You only have a closer look to the methods you want to use. The new CITS technologies are used most of the time, of course, in R&D projects, and most of the time in Germany, it's Düsseldorf, Hamburg, Hannover, and so on. What we also did next to the CITS methods, we implemented a real-time communication in the signal control, just to make sure that we can have the information comes from the RSU as fast as we can get it, and also for the cloud. And this is also useful for a lot of applications. You can think about that. Then the integration of CCAM information in the signal logic was done by messages, by a definition of specific messages. So you can use that information in form of a function, and the information is directly in the control itself. There's no usage of an additional detector input or so, or AP values from an OSIT connection also necessary right now. Then you can use also the public transport, the old containers like R09, I only know the German one for that, and traffic light control, and also the digital ones, which is part of SRAM and SSM. And next to that, of course, we are thinking about the aggregation of methods here of CITS messages. In my opinion, we did the step that we brought that information of the connected cars to a next level. Means that we don't talking about data, we're talking about information which is in that data, and that information you can use as always directly at the decision points of your signal control. So it's more like a toolbox for me, and if you bring the toolbox to the customers, the customers will find really cool and high sophisticated new methods. And if we see that there's some kind of a trend or whatever, you can also use it, or we will also bring up some aggregation of methods and support of many more messages here, just to make just to make sure that they can do the best with the information we have. Maybe you have some questions, and we have a small round, so feel free.
Yeah, thank you, Mario. There is already one question, two questions from Sirwan. Mm-hmm. One of them is, do we need extra Visum API add-on to test V2X?
No, you don't need that. It will be part of the conventional Visum. There's no extension needed.
Great. And the other question is it possible to test these CITS functions in Sumo?
This is a really good question. If you're familiar with some programming, you can. I'm sure you can implement it directly. For now, there is no support, no direct support for the customer to do that, but we're thinking really strong about that. We will have export for Sumo, and of course we will have we will see it there. But if you're familiar with Sumo, you see the power of that API, and I don't think it's really a high problem to implement it if you want it.
Okay, great answer. Because last week it was in DLR because of one projects, and they said that they are already implemented an API for testing Lisa Plus logics in Zomo. Therefore,
yeah, we know that. We know that extension. Yeah, it's Lisum. Yeah, we know. But you have to make sure, because I'm sorry for that, for that interruption. On the one side, you have Sumo, which is a traffic micro simulator, and on the other side, you have Lisa, and there's development going on the Lisa side as well as on the Sumo side. And then there is some middleware, which is called Lisum, which makes the connection between those parts. And I think we should talk about that in the future, that we bring the two worlds together, because that middleware will be sometimes it will be outdated.
Okay.
Because of the two development lines you have here. Yeah.
Okay, it's exactly like that software that we need to install for Vizim, Lisa to Vizim.
Yeah, exactly. This is the same. Yeah.
Okay. But it would be in future something like that to install and use it without problem, hopefully.
Yeah. What I'm seeing here is as a traffic planner, you write some code. It's your code. It's unique, and this is your part. And why should we tackle that? That you can use a simulator like Sumo, AIMSA, or whatever. So in my opinion, I think this is just we have to talk to each other, and I think this is solvable. And in the future, of course, I see a Sumo connector as well.
Okay, because it's also interesting for me for some of projects. We have also some other projects, CITS projects, and we are trying to use Lisa Plus as a control logics for CITS and autonomous vehicles and information from the vehicles. But it was really nice, informative, and interesting.
Well, thank you. Yeah, just talk about that. If you have R&D projects or whatever projects, maybe with the DLR, we also know that, guys, so it's no problem.
Yeah, we are already into testing different softwares and to see which software we use. And for one of our projects, definitely Lisa Plus is really user friendly. Definitely we use that, and we are waiting for Lisa 8. Definitely. And yeah, we will talk maybe later about projects also. If we had problems, definitely I will contact with you or Mayuk.
Yeah, the good things with projects and maybe with R&D projects and so on, we can have the development maybe you need for the future. You see the point, or?
Exactly. You get the points. It's a really nice point. Okay, then if there's new information or something about that for R&D, then would you please send to me more information if there is new developments in Lisa Plus or something like that?
We have a newsletter. Maybe on the next. I don't know. Or maybe stay in contact with Mayuk. I think you will have the perfect one to answer all your questions.
I will do that.
Great. Mario, I have a question regarding the slide you were showing the differences between the position of the
you mean
request.
That one? Is it that one? Yeah.
Yes. So here, one of the data that is shared with the controller is the speed, isn't it?
Yeah. It is shared here. This is this one. I'm sorry, I should bring a headline here. Here we have detectors. You see it here, that rectangle here, detector, detector at different locations. And in that case, we don't have a detector, or maybe we have detectors, but we only use that value here, that equipped car here, and the number which is on here is it's also the computed time of arrival. The car itself knows the position, so then it can do map matching, and it knows the current speed it has. So you can do a computation of an estimated time of arrival. You can do it really simple, just by division, velocity, and time, or you can do it more, yeah, more sophisticated. I would call it like that, with deceleration movements and so on and so on.
But for example, if this vehicle is has 12 seconds of estimated time of arrival,
Yeah.
but the approach is congested,
Yeah.
and maybe those 12 seconds won't be will be more.
You're totally right. The 12 seconds means that there is no car, there is no queue, there is no car starting their engine and crosses the border. You're totally right. The computation of estimated time of arrival is really complex, and it depends on so many things. Absolutely right. And of course, a jam is a jam. I would call it like that. If you have connected cars which are all in the jam, an intersection won't handle that. But you see, if the degree of freedom, I would call it that, if the degree of freedom of intersection is high enough, because you have less cars and really far away from each other, you can have really cool intersection logics, which are really actuated to that single cars here. But if it decreases, you have more strategic operations here, just to make sure that the coordination will work as expected and so on.
Okay. Yes, no, because this would be a specific case, for example, for an emergency prioritization, because there is just one vehicle in the approach, but the lane, the link is congested, and there are many other factors. But okay.
And
so in the estimated time of arrival, it is taking the traffic state, the speed, and so on. Okay.
You can do it much more complicated if you want. As an intersection, you can observe the traffic here as long as you want. So it means you get a lot of data sets here. Maybe you can learn from that. If you see that it's a car here with that speed and that traffic situation here, you can see over time what is the estimated time of arrival with that specific traffic scenario. So you can over time be better for emergency vehicles. This is a great thing you're talking about. For emergency vehicle, one thing is, of course, floating car means you have the position and you get the speed of the car, and just you want to make sure that it can crosses the intersection without a queue or whatever. This is just the position. This is the one approach. The disadvantage of this approach is that you don't know the route of the emergency vehicle. It can go right, straight, left, or maybe it makes a turn. You don't know. If you use CITS, I would prefer to use SRM and the SSM concept, because if you bring it to the emergency vehicle, you can first of all transmit if there's a siren on or not. Maybe this is important. The next part is that you can do a request to a specific signal light, not only for the approach, means a lot of signals here, means for specific directions, and then you can make sure, okay, intersection, just make sure that all the vehicle should cross that intersection, and don't stop everything which is here, or just open the whole approach. You can do it much more finer if you use other information sources here.
Okay, perfect. Thank you.
Thanks a lot for joining us today. And as always, we are at your service if you have further questions. Please contact us at service@schlotauer.de if you have any technical questions, or if you want a quote, an offer, have any sales related questions, then please contact us at lisa@schlotauer.de. Thanks and have a nice day.